Please
Okay.
invite Professor Baras
Of
on stage.
course. It's a great privilege for us this evening to open our first kick-off conference of the inaugural Invention on Space Economy with Professor John Baras. Professor John Baras is a distinguished professor at the University of Maryland, College Park. He holds the Lockheed Martin Chair in System Engineering and a permanent joint appointment with the Institute for System Research and the ECE department. He received a PhD degree in applied mathematics in the Harvard University. From 1985 to 1991, he was the founding director of the ISR, and since 1992, he has been the director of the Maryland Center for Hybrid Networks, which he co-founded. He is a fellow of IEE, member of the National Academy of Inventors, and a foreign member of the Royal Swedish Academy of Engineering Sciences. He has received major honors and awards. He has been awarded 20 patents and honored with many awards as innovator and leader of economic development. Also in June 2018, he was awarded a doctorate honoris causa by his alma mater, the National Technical University of Athens in Greece. Professor John Baras is also in the advisory board of the Greek Scientist Society. And his research interests include systems, machine learning, artificial intelligence, communication networks, applied mathematics, signal processing and understanding, robotics, computing systems, network security, systems biology, model-based system engineering. Professor John Baras, thank you for being with us this evening to discuss about space and why to love space. Please, Professor, you have our full attention.
Okay, so thank you very much for giving me the opportunity to speak in this inaugural meeting. I want to talk about a subject that is, as you will see, why very deep in my interests, and it has to do with the role of space in many aspects of life, economy, and society. That's an area I've worked on for more than 30 years. And it involves many of the areas that I'm interested in particular autonomy, communication networks, and certain aspects of computing. So the main thing that drives our research in this area is what we call the problem of ubiquitous access and connectivity. And sorry for the typo on the title. The issue is that although we have lots of data, only about 15% to 20% of the population on the Earth has broadband access to this data. And now we know that if we don't have broadband access, we cannot take the location of out of the considerations for work, health, and many other aspects of life. So one of the main drivers of the importance of space is that we believe in Maryland, and so do other people, that without the involvement of space, namely satellites, we are not going to be able to eliminate the digital divide. And we actually doing experiments to demonstrate why this is so. So this issue of ubiquitous access and connectivity and the lead to hybrid networks has been identified and has been also identified with ESA. So what we mean by hybrid networks is the picture you see, meaning satellites, terrestrial, wireline, and wireless networks interconnected and serving people in various things they want to do. So the digital divide is a very big problem because in addition to dividing on the basis of economics, it also divides on the basis of what jobs you can do, what education you can get, what healthcare you can get, how you can move around, and so on and so forth. And typically the areas that are underdeveloped or rural are left out of this progress. And if we don't attack the digital divide immediately and effectively, this so-called inequality will keep increasing. And as a proof that the European Union has understood that, there's this announcement that was not very recent, but it's from February of 2022, where the European Union announced 6 billion satellite system to close the digital divide. And what we mean by that is that the satellite systems must work in synergy with terrestrial wireline and wireless networks. So what's going on? We all have access, at least in major cities, to broadband access, hundreds of megabits per second, and More than that, we have them in our offices, in homes, and so on and so forth. And then you have lots of densities of these users, and therefore there's a scarcity of bandwidth sometimes. There are issues with privacy and security, which I will not go in detail, but I'll mention them. But they are basically, these networks are permeating everything we do, from going to the gasoline station and paying your bill to actually communicate with your doctor and so on and so forth. All right. So 5G, which is the current technology that is being deployed in wireless networks, has promised enhanced mobile broadband, ultra-reliable communications, very small delay, and massive machine-type communications. Has it happened? No. And there are many reasons why it hasn't happened as broadly as expected. But the reason, in our opinion, is that the wireless networks themselves cannot solve the problem alone. They have to collaborate with help from space. So the purpose of this slide is to show you that there are many technologies that they have to come together to give you the dream of 5G. And in addition, that brings convergence even for terrestrial wireless in terms of millimeter wave, Wi-Fi, okay, many other technologies, and most notably, the virtualization of networks via software-defined networks and network function virtualization. And that's important because you will see in the very last slide why this is important for both Greece and Cyprus. Okay, so in essence, 5G then becomes a network of networks. There's the wireless, LTE and 5G, there are the Wi-Fi, there are many others, and now there are also the satellites. And that's a slide that a lot of people use that shows you that the dream here is that you're going to be able to use this network to help autonomous cars, autonomous ships, education, healthcare, sensing, and many other applications. And this is the various areas where the so-called IoT, Internet of Things, is being pursued. And some of them I will touch upon, which are important for Greece and Cyprus, namely agriculture, merchant marine, smart cities, and health and education and transportation. Okay, so this is the 5G perspective, and what you see here is that the three major things: enhanced mobility broadband and massive machine-to-machine communication. On the right slide, the pictorial shows you that if you do this properly, then the society has a lot of mobile connectivity, and many of the things that you dream about, you can do. Okay, so the thing that perhaps not everybody is familiar with is that what has happened in terrestrial optical networks is the network, thanks to software-defined networks, or SDN, and network function virtualization, or NFV, has been virtualized. We sacrificed efficiency to be able to have very fast deployment of networks on demand. And this creates, of course, benefits and challenges, but everything becomes now an automation problem. The management of the network, who you give resources to, what delay you accomplish, and so on and so forth, it becomes essentially an optimization and control problem in almost real time. And this creates a lot of challenges, and it's even more challenging when you try to extend it from the fiber to wireless and satellites. Okay, so what is happening in satellites is that many of you know that we have satellites now that they have extremely high bandwidth. They may have many beams on board, so they can actually communicate with different parts of the Earth. And we have low Earth orbit satellites, which are called LEOs, we have MEOs, and we have GEOs. And people have been trying for several years now to see what the role of satellites will be in 5G. And there has been progress in this, including actually some demonstrations of how this can play well in many areas of economy. So where I started with this and why this area is so dear to my heart is that almost 20 years ago, with Hughes Network Systems, we were the first to demonstrate Internet over satellite in our lab in Maryland, and this became the birth of an industry which now is about 10 billion a year around. And whenever you fly and you use the internet over an ocean, you should remember where this started. Okay, so this led to a tremendous development of products which won many awards from Hughes, and you can see them here. And we are again working with Hughes and several other companies to try to extend these ideas to 5G and 6G. This is a protocol we invented for doing TCP over airplanes. And the note you see on the right-hand side is a very recent one where SpaceX, which you all have heard about, is now linking and using their satellite networks to provide online connectivity with via Starlink with the aircraft. But now this is happening through LEOs, which has an advantage because the delay is much smaller than the GEO. This pictorial is trying to show you that because the satellites cover large areas and many things happen in these areas, that it can affect many times, even things like smart mobility, parking, moving ships, electricity, smart grids, and so on and so forth. I won't have time in my short period here to go through all this, but I'll try to tease you a little bit. So this is showing you, again, why satellites are becoming important for this infrastructure. And the bottom right says that in order for this to succeed, the satellites have to become part of the virtualized network. Okay, so the entire network now is becoming virtual. And these are some of the things that I got from a report that satellites can offer together with terrestrial wireline and wireless networks in urban areas and in rural areas. And many of them are very, very useful things. And they are useful for life, but they are also opportunities for economic development, starting companies, etc., etc. Okay, so these are the 4 categories that I have quite a few slides, which most of them I will skip. They are trunking and head-end feed, backhauling and tower feed, communications to the move, and hybrid multiplay. Okay, the things we're examining right now is to actually find out what a typical household needs in terms of bandwidth and requirements of delay, and so that by combining satellites with terrestrial wireless, we can actually offer this service to more people at a lower cost, which is always what we want. So this is a slide to show you what is trunking and head-to-end. I'll skip some of these things. This is backhauling. This is communications on the move. The talk will be posted. This is more to give you a point of reference. And then satellites can achieve sub 1 milliseconds latency if you do it right, and if you do not go too deep into the architecture of the network. And you have space-enabled 5G services, you can see here, and many others. Okay, and many of them involve, things like transportation and other services. And this is sort of a roadmap that I got from the ESA report, the European Space Agency. So ESA is very much into this, and they have invested actually. This is the project they started on satellite and 5G, and this is the architecture that they have advocated to cover the 4 cases I just described. Okay, so when you virtualize the network, this is not an easy exercise, but what happens now, everything becomes more automation and software problem. The hardware is sort of secondary in this need. What we are doing in Maryland, we are studying very heavily this architecture, which is SAGIN, meaning satellite and ground networks. And you can see here, in addition to satellites, you see UAVs and other objects that they fly and things on the ground. And we are trying to extend the software-defined network to this architecture to be able to give people on-demand networks using this infrastructure and satisfying the bandwidth and delay requirements they may have. One problem that comes that we study is the joint placement of UAVs and traffic routing in these multiple networks. Why you want to do that? These needs may appear because of agriculture or because you have lots of people and they need bandwidth and you don't have enough and you want to strengthen them, strengthen the bandwidth resources, as it quite often happens in rural areas. Okay, and then you have also a joint satellite gateway placement and the routing. Because in order to communicate between the satellites and the terrestrial networks, you have to have something that's called gateway. And the gateways are not everywhere because that becomes very expensive. You can have, for instance, a gateway for a few houses. You can also have direct to the house communication. But the gateways are a very efficient way to spread this architecture much better. And then, therefore, there's the problem of where do you put the gateways and what's a good and efficient way. This slide is a little bit more technical. It basically uses the term network slicing, which is plain language means I want to create dynamically sub-networks from the structure you saw, And here I show you one slice, one subnetwork for smartphones, another one for autonomous vehicles, another one for massive IoT, and so on and so forth. Okay, and that's a very difficult problem. On top of that, now we have all these humongous constellations with LEO satellites with extreme capabilities. Then you see some pictures here. That two of them are almost completely done, meaning that the satellites have gone into space. And these satellite constellations, the goal is actually to provide broadband to everybody on Earth and give them many of the services that we enjoy in only about 20% population of Earth right now, even in the advanced countries. And there are many of those that I describe here. Okay, and this is an architecture that people have thought about, where you can actually have GEOs, LEOs, MEOs, and terrestrial working all together towards this network. Okay, and the nano and micro satellites that Theo mentioned actually are a means by which you can democratize access to space, and this is important for both Greece and Cyprus. Now I'm going to go through very quickly through a set of applications that I selected because they are important for the economies of both Greece and Cyprus. The first one, of course, is merchant marine. This is perhaps the most important part of the economy of Greece, and these networks can help in many ways in terms of monitoring the ships, providing security to the ships, moving them around, as I see here, and moving the cargo and the crews around. The second area, which is also a large part of the economy, both in Greece and Cyprus, is agriculture. And agriculture is becoming completely mechanized, but it cannot be mechanized without communication. So you have these hybrid networks that they help the tractors, who can be roboticized. You can actually have both pictures from UAVs and satellites that they can detect diseases in the plants. They can detect the condition of the soil. They can detect many things and help the farmers to do the job much easier and more productively. And you see that Nokia, which is a telecommunications company, is focusing on this area for the reasons I just mentioned. Another area is to monitor the environment, and you monitor the environment in terms of looking at whether you have erosion in the beaches, whether you have destruction because of physical phenomena, or you can find examples where in lakes and other places you have pollution beyond what you would like to have. And this has been, of course, led to several satellite systems, and you see some of them here. And NASA has spent a lot of money to actually have their own satellite systems. The next area is smart transportation, where basically I want to have these autonomous cars. And you can see here on the left an architecture that tells you how satellites and terrestrial networks can help the autonomous vehicles. On the right, you see the famous picture that basically vehicles communicate among themselves, so with the infrastructure, and they can actually go around and so on and so forth. And this is the picture that is emerging with respect to these smart transportation systems. And one of the things that we worked with is try to use these communication infrastructures to do cooperative highway merging and also do shockwave absorption so that you don't get congestion. I want you to notice the left-hand side of the slide where it says this architecture can actually help us to create smart fleets of autonomous robot taxis. And my proposal here, if we do that, to give them free. You don't pay anything. And if you do the cost analysis, you will find that this is a winning proposition.
Professor Baras, if I may interrupt, we just passed the 7. Please take your time before we move to the next panel. Thank you so much. Sorry.
Sure. There is a hub networks in healthcare that you have networks that they follow the monitors that you have, like I see here. And you have extensive telemedicine, which is also a very important thing because with these methods, you can actually give high quality and low cost healthcare to everybody, which currently doesn't exist in Greece and in many other countries. This is an example of a information highway we built for the diabetes mellitus. And there is only one country in Europe that has a complete medical information highway, that's Finland, and the US, only Massachusetts, is coming close to do anything like this. And then you have education, and there are several slides to say how these technologies can help in smart cities, which actually now we know that if we don't make them sustainable and provide the services, then they will not survive. And we're already seeing a sign of this to cities above 2 million that they get to deteriorate. Let me finish. This is disaster relief, which you can use again the hybrid communication. It has been used in several places to reestablish communication. And let me skip these things and go to the end. All right. So And then there's, of course, defense applications, like you see here, where you build UAVs and ground forces supported by satellites for the Navy, the Air Force, for the Army. We've done a lot of work in this area for monitoring what's going on and also, controlling your forces. These are very well developed things. And if you want more exotic things, we are looking at communication architectures in space, going to the moon, and even beyond with these architectures. And we have, let me close with this lab we have in Maryland, where we actually build space robotics, thanks to Professor Aiken, that go directly to the space station. And again, these communicate between themselves and also communicate with the humans. All right. Now, this is the last slide. Why these things are important for Greece is because they're centered around information technology. And as I said many times before, this is a perfect opportunity for Greece and Cyprus to excel, because information technology does not require a lot of resources, they require brains. But it's so important as the other 5 applications that I show here in terms of changing the world completely. Thank you very much.
Professor Baras, thank you very much for this informative introduction. We will now continue with more on this matter with our 2 panels. We will reconnect with our first panel discussion, and I'm sure we will have many more to discuss after September in the next conferences to follow up about space. Thank you, Professor Baras.